The unit of concentration that chemists use probably the most is called molarity. Because if you haven't noticed, we use moles a lot in chemistry because in the balanced chemical equation we're relating numbers of particles to numbers of particles, and mole is a counting unit. And so it's convenient many times to use moles in a concentration. So molarity, which is abbreviated capital M, is defined as the moles of the solute divided by the liters of solution. So again, it's solute over something with solution. So not the volume of the solvent. So when you're making a specified molarity, you usually put the solute into a flask. You figure out how many grams you need to give you the correct number of moles, and then you add water. Because we're looking at the total volume of the solution. So here's an illustration of how you might make a solution. Here we're making 1.00 molar sodium chloride solution. That could be abbreviated 1.00 capital M. Capital M's and lowercase m's can look alike, so when I write them by hand, I always underline my capital M's, and that means 1.00 moles per liter. So we need 1 mole of sodium chloride, so we do a calculation to figure out that we need 58.44 grams. That would be using the molar mass. So we weigh out 58.44 grams of sodium chloride, we put it in a volumetric flask. This is a flask that's designed to hold a particular volume, in this case 1 liter. We add some water, we get that to dissolve, we mix it up a bit, and then we continue adding water until we get the bottom of the meniscus right at that line on the neck. And then you would have to cap it and invert it like 20 times to get it to thoroughly mix. Now we have 1 mole of sodium chloride dissolved in 1 liter of solution. Let's calculate the molarity of a solution made by putting 55.8 grams of sodium nitrate into a beaker and diluting to 2.50 liters. So we've got 55.8 grams of sodium nitrate, and we've got 2.50 liters, and they're asking us for molarity. So we need to remember the equation for molarity. It's not too complicated, but it's moles of solute. I'll start that one over. Moles of solute per liter of solution. And it has to be liters. It can't be milliliters or something else. It has to be liters. Moles per liter. So this tells us what we need to find. We need the moles of solute and we need the volume of solution in liters. Well, do we have any of those? They gave us one. Which one? You guys have to wait. 2.50 liters of solution. Y'all stayed up way too late studying last night, didn't you? You're half asleep. We've got a mass of solute, we need moles. So we need to calculate the moles by using the molar mass of sodium nitrate. So for sodium nitrate, we've got the mass of 1 mole of sodium plus the mass of 1 mole of nitrogen plus 3 times the mass of oxygen .85. Is that an exact number? No. But my calculator just said 8.5. It's like when you go to the grocery store and it comes out to be $100. Exactly. You're like, whoa, maybe I should buy a lottery ticket or something. This number is not exact. Based on how we calculated it, it should have 4 significant figures, so we have to put the zeros in because the calculator doesn't understand. Grams of sodium nitrate is equal to 1 mole of sodium nitrate. So 1 mole of sodium nitrate weighs 85.00 grams. The unit gram cancels out. So we've got 55.8 divided by 85. 0.656. There's my last significant figure. Write down 2 more moles. I don't want to round this yet because I'm going to use it in another calculation. I see you guys doing this on your lab reports. If I round this off now and continue on with a rounded number, I'm probably going to introduce some error in my final result. So I'm indicating where the last significant figure is, but I'm going to carry those 2 extra digits with me. You don't have to carry all of them. Just carry 2 extras. So I'm going to put this in here. This is my moles of solute. So it's that divided by 2.5. And I get 0.262. There's 3 sig figs. 58 moles per liter. Rounding that off, I get 0.263. You can write it as moles per liter or 0.263 capital M. Any questions? Molarity is an excellent conversion factor. It allows us to convert between moles of solute and liters of solution. So when we're doing a chemical reaction, instead of looking at masses, we can actually take a solution and just measure the volume. And okay, we've got 10 milliliters of this, and this is its molarity, and we've got such and such of this, and we put them together. We can do this calculation to find out how many moles of a substance we added. So let's see how many grams of sucrose are contained in 1.95 liters of 0.781 molar sucrose solution. When you see this capital M, it's more convenient to type that on the computer, but when you write it out by hand, what often happens is students forget that capital M stands for moles per liter, and they somehow translate that just into moles or meters or something other, and they have a problem. So when you write this down, write it down as a fraction, moles over liters. And that should jump out at you and say, I might be a useful conversion factor. Does it say that to you? Not at 8:30 in the morning, it doesn't. And then I've got this number, right? And I'm trying to find grams of sucrose. So for my path here, I've got grams of sucrose at the end. And what am I starting with? The liters or the moles per liter? The liters. I'm going to start with that volume. So I'm starting with 1.95 liters of solution. And I'm trying to get to grams of solute, grams of sucrose. What does this allow me to convert? Liters to moles. So using this, I can go from liters of solution to moles of sucrose. Could I go from moles to grams of sucrose? Sure. I need the molar mass. They gave me the chemical formula. I can calculate that. So 1.95 liters times Next up is moles of sucrose. And liters is going to go down there to cancel out. And the next fraction is grams of sucrose. And we're going to divide by moles. .781 moles per liter. So that goes right here, 0.781 moles per liter. And then I need the molar mass of sucrose. I'm surprised I don't have this one memorized yet. That would be 12 times 12.01 plus 22 times 1.008 plus 11 times 16, 342.3. That's the mass of 1 mole of sucrose. So I just do the math. And I'm getting 521. 3 sig figs, 0.29 grams of sucrose. And so that would round to 521 grams. Any questions? Does that number seem reasonable? It's kind of hard to tell, huh? Here, 1.95 liters, that's almost 2 liters, right? 2-liter bottle of soda. So this is significantly more than the previous example where we were looking at a can of soda, but the volume's also larger. Any questions? How much of a 0.225 molar KCl solution contains 55.8 grams of KCl? What is the thing with 55.8? Well, let's write down numbers. 0.225. Instead of writing the capital M, write moles over liters. That's moles of KCl per liter of solution. And then we've got this guy over here, a mass of KCl. So which number are we starting with? The 55.8 grams. So 55.8 grams of KCl, and what are we trying to find? How much solution? That's a poorly worded question. I didn't write it. It's the volume. How much solution would be a volume? What would be a convenient unit? Liters. So we want liters of solution. What do we need to go to in the middle here? Moles. So we go to grams. Grams of KCl to moles of KCl using the molar mass, and then moles to liters using the molarity. There's a TV show called Malcolm in the Middle, right? In chemistry, it would be moles in the middle. When you're doing setting up this conversion path and it doesn't look like you can connect the ends, try moles. It's usually there in the middle. Once you have the path, it shouldn't be too bad, 55.8 grams of KCl to moles of KCl. And we're going to have grams down here. And then we're going to have liters divided by moles of KCl. So this is our conversion factor for one of these. Moles to liters, 0.225. So this time it goes in the bottom, 0.225 moles in 1 liter. And then we need the molar mass of KCl. So that's 39.1 plus 35.45, 74.55 grams of KCl is equal to 1 mole. So 55.8 divided by 74.55 divided by 0.225. 3.32. Write down 2 extra digits, 66. And that's going to be liters. And then we look at rounding, and we get 3.33 liters of that solution. Any questions? If you can do dimensional analysis, it saves you a lot of thinking later. This isn't the only way you could solve this problem, but I think it's the easiest. When we report the concentration of a molecular solute, that reflects how many moles of molecules are in a given volume, right? Because molecular substances do not separate into ions. If we have an ionic solute, though, when ions dissolve in water, they separate, right, from each other. And so we need to be a little bit careful if we're wanting to know how many moles of an individual ion we have. So if we had a 1 mole per liter calcium chloride solution, what does calcium chloride do when it dissolves? Calcium chloride dissolves into ions. And there's 1 calcium ion, and then there's chloride ions. How many chloride ions? 2. This tells us there's 2. So there's 1 calcium ion and 2 chloride ions. So in 1 liter of a 1 molar solution, we'd have 1 mole of calcium per liter and 2 moles of chloride per liter, because it comes apart. Okay? So determine the molar concentrations of calcium ion and chloride ion in a 0.75 molar calcium chloride solution. So 0.75 moles of calcium chloride per liter. What I want is the molar concentration of an individual ion. So what I want is I want how many moles of calcium ions per liter of solution. So this is liters of solution. The conversion factor here actually comes from the formula. I need moles of calcium ions per mole of the whole thing, calcium chloride. I have moles of calcium chloride per liter of solution. I want moles of calcium ion per liter of solution. I look at the balanced chemical equation. I look at the chemical formula. There's 1 calcium ion in 1 mole. 1 mole of calcium in 1 mole of that substance. So that's 1 to 1. The calcium ion concentration is the same as the whole compound. If we're looking for the chloride ion concentration, we're looking at how many moles of chloride ion per mole of the compound. Well, what's this relationship? How many chlorides in the formula? 2. So this is 2 moles of chloride for every 1 mole. And this is going to be 1.5 moles of chloride ion per liter. So here I've demonstrated how you can do this using dimensional analysis and looking at the units. This one is easier to think about, so you could also just look at this and say, oh, well, there's 2 chloride ions in every one of these, so I just need to multiply this by 2. But you could do that also if it makes sense to you. Any questions?
When they get more complex, like there's like 3 elements on one compound, can you do that as well?
Yeah. Yeah, you can do it if you had, 3 different elements, or we're never going to have actually 3 ions, but you could look at how many moles of, yeah, we're actually never going to go there. You'll have 2 ions only in Chem 3A.